Hi, I'm Jamal.
Hi, I'm Michael.
Today we're presenting the final project on AI-generated text detection. With the rise of ChatGPT, it has become increasingly common for students to use AI tools to write essays. Our project aims to develop a machine learning model capable of identifying whether an essay has been written by a student or generated by a large language model. For datasets, we have a training dataset consisting of 2,762 essays. This dataset consists two parts: 1,300 from Kaggle, mainly written by students, and 1,300 essays generated using Google's PaLM model. Additionally, the hidden test dataset consists of 10,000 essays to test our model's ability to perform on general datasets. Though different embedding method, but we have the same tokenizing approach. And let's hand over to Michael.
With tokenizing, we have all the data stored in the list, and then we pass the list into a new data structure called vocab that takes in this list of tokens and then count the frequency per word. It is basically a dictionary that takes in any word we have and then return the frequency of this word. With punctuations or symbols, we'll simply use unknown instead. Okay, then I'll introduce the RN model. RN block is very essential block in modern natural language processing models in general. We have this data set of 30 articles per batch. We use the one-hot encoding to encode all the articles. We store the information of articles into a hidden state. Before that, we'll initialize the hidden state with a corresponding prompt. And then we'll treat each article as a time step and return the output, the prediction per time step. We'll use cross entropy loss and atom optimizer. As you can see here in the graph, the loss of training dropped from around 0.7 to around 0.3. However, the training accuracy is finalizing at around only 0.57. And then BERT.
The second approach is BERT model, which stands for bidirectional encoder representations from transformers. As Michael mentioned earlier, we begin by tokenizing and padding the given text, and then we embed each token with its learnable position code before passing in the 8 encoder blocks. With each encoder block, it contains a multi-head attention pool of 4, so that the model can extract features from different parts of the input sequence containing 512 tokens. We then pass the final output of the encoder into 4 fully connected layers to output the binary classification label. For training, as shown in figure 2, the accuracy quickly rises to over 80% within 10 epochs, and the loss stabilizing around 0.36. However, when we put it to the test on Kaggle, the score drops to 0.612, indicating a gap between predicting on training data and the general testing datasets. A potential reason could be the imbalance in our training dataset, predominantly composed of essays generated by Google's PaLM model, so that our model is overfitting to the specific characters of PaLM generated text and not robust to general testing datasets. And for conclusion,
I'll do the conclusion here. So we use RN and BERT models to solve this problem. With RN, we have great training loss. We drop from 0.7 to 0.3. However, we have not so good testing score and very low generalization ability, mainly because we use an article instead of a sentence as a time step, which is too much information for a hidden state. Solution is to use trainable embeddings instead of only one-hot encoding, which has high efficiency in storing information, so that we can change the time step from an article to a sentence. Also, we can generate an output per time step so that we can update the weights more frequently. With BERT, we have a great training and testing score. However, we have a great, huge generalization gap, which we can also see that from on predicting on unknown datasets. The solution is to probably use additive attention instead of dot product attention. We can also lower the layers of multi-head attentions. We can also use dropout layers and regulations in the linear classification blocks to lower the generalization gap in order to better the model's ability in predicting unknown datasets. That is how our models work on this AI-generated distinguishing problem. And thank you.
thank you.